Okay, so welcome back. Now here's the theorem, the mean value theorem. So it says let f be a continuous function. Let f be continuous over the closed interval ab and differentiable over the open interval ab. Then there exists at least one point c in the open interval ab such that f prime of c is going to be equal to f of b minus f of a divided by b minus a. In other words, the slope of the tangent line at c will equal the slope of the line that the secant line that connects the endpoints. Okay, now here's the proof. So let's consider. And again, keep in mind that Rolle's theorem sets the stage for what we're going to do. Okay. So the proof follows from Rolle's theorem. Okay? And so let's consider the line connecting the endpoints. So consider the line connecting a comma f of a and b comma f of b. Now, since the slope of the line is this, so since the slope of this line is f of b minus f of a over b minus a. Okay? And the line passes through the point a comma f of a. Right? We can write the equation of the line. As y equals, well, the slope is going to be this. Excuse me. Okay, so it's going to be y equals mx plus b, so it's going to be x, and then so this will be the slope. Oh, right. So this will be x minus a, right? Because we're talking about some value that's away from a plus plus f of a. Okay, so that's the equation of the line for the secant line. So now what we're going to do is let's create another function that represents the vertical difference between the point x f of x, right, and the point x y on the line, right? So we want to denote that, hey, if we have something like this, let's say we have the line, right, that connects A and B. And let's say we have another line that does something like that. We want to represent another function that represents the vertical distance between F, the point on F, and the point on Y. Okay, so this difference, this is going to be g of x. Okay, so we're going to define g of x that way. Okay, so let's continue. Okay, so now we're going to define g of x. So let g of x denote the vertical difference between the point x f of x and the point xy. Okay, so now here's y represents the secant line, right, that connects the two endpoints, right? And we want to denote g of x to denote the vertical difference between a point at x comma f of x, a point on the function at x, and the point on the secant line at the same value of x. Okay, so that'll give us the vertical difference. Okay, and so we're going to define this vertical difference as, you know, a subtraction. Okay, so in other words, let me erase this. I don't want to erase what I have down here yet. Okay, so in other words, we're going to define g of x as the difference between them. Okay, so it's going to be f of x, right, minus y. Okay, so it's going to be f of x minus y, which is going to be f of x minus f of b minus f of a over b minus a times x minus a plus f of a. Okay? So that's going to be g of x. Okay, now, since the graph of f intersects the secant line when x equals a and x equals b, we're going to see that g of a equals 0 at the endpoints, right? So obviously that makes sense, because then the vertical difference at those points is 0, right? Where the two graphs are going to intersect, it's going to be 0. Okay, so let's write that. Okay. Since g of x intersects, what else should I say? No. Since since f intersects the let's say, oh yeah, it intersects the secant line at the endpoints, g of a will equal 0, which is going to be the same as g of b, right? Okay, so that's what I'm saying. Now, since f is a differentiable function over the open interval, g is also a differentiable function over the open interval. That's also obvious, right? Because g is defined in terms of f, right? Y is determinant of f. Okay, so that makes sense. So let's write that. Since f is differentiable over the open interval AB, so is g of x. And then furthermore, since f is continuous, over the closed interval AB, so is g of x. So g of x is differentiable over the open interval AB and continuous over the closed interval AB. So therefore, g satisfies the criteria for Rolle's theorem. Aha! So hence, g of x satisfies the criteria for Rolle's theorem. Now, what? Now, okay, so before I go on, now notice, g of x is continuous over the closed interval AB. It's differentiable over the open interval AB, and g of A and g of B are the same. Okay, so now, consequently, there must exist C in the open interval AB such that G prime of C equals 0. Ha ha! There it is. There it is. Right? That is key. So, and let me show you why. Okay. Since g prime of x is equal to f prime of x minus f of b minus f of a over b minus a. Okay, now where did that come from? Well, this comes from taking the derivative of this, right? So g of x is equal to this, so remember these are continuous differentiable functions, right? So if I take the derivative of g, well that's just taking this derivative termwise, so this becomes f prime of x. This here just becomes 1, right? Because here, this is a constant, right? This is just evaluated at a and b, so this is just a number. This is just a constant, so this becomes 1. And this is just a number, so that becomes 0. So we're just ended up with this. Okay? So now, that means g of c, g prime of c I should say, g prime of c is equal to f prime of c minus f of b minus, f of a divided by b minus a. Again, this is just a constant, right? So now all I do is plug in c in place of x. Now since g prime of c is equal to 0, guess what? F prime of c has to equal f of b minus f of a divided by b minus a. And that's the result we were looking for. End of proof. So we just showed that there exists a c in the open interval AB such that f prime of c is equal to the slope of the secant line that connects the endpoints. And that is the proof of the mean value theorem. Have a great day.